Hello, operating systems people. This is Gabriel Palmer, and today we're going to continue our discussions about file systems and continue by talking about the devices that actually underlie them and why they are really cool but require a lot of complexity from the operating system standpoint. So we've talked about many things so far. We've talked about how operating systems need to provide file systems, and those provide abstractions and interfaces. The file system, the virtual file system layer, the VFS layer. We've talked about how to make these abstractions somewhat efficient, but today we're going to talk about specifically how to make them efficient for magnetic disks, going a little bit further than we talked about yesterday, although I am going to be leveraging the fact that you already listened to kind of the physical characteristics of disks, and we're going to go further, talk about solid state and flash drives. I was not, as last time, howling at the sky with Penny, so hopefully, I won't sound like I'm dying throughout this entire talk. And I have water beside me, so, setting myself up for success this time. All right, so what I'm going to be talking about is optimizing for the physical devices, right? And by that, I mean like the physics of those devices. I'm not going to go into how they actually work on electrical engineering, from an electrical engineering perspective, largely because I don't know. So I will let you seek out other sources for that. But I do know the abstractions and what they imply for the operating system. So we've talked about rotating mediums, so magnetic disks, and we talked about them having head seeks that are very, very slow, and you can get very, very low throughputs of data out of disks when the head needs to seek. However, they're relatively faster for rotation. And today we're going to talk a lot about solid-state disks, which have kind of various properties that are also esoteric and strange, especially around erasure blocks and wear leveling. So let's dive in. So let's first look at reads, because reads are fairly unambiguous and easy. There are two dominant flash architectures, NAND and NOR. They're named after, the NAND logical structure or the NOR logical structure. NAND are the dominant devices today that you would think about buying. NOR might actually be more common because it's in a lot of microprocessors. But NAND is what we're going to be talking about today. So if you kind of look them up on Wikipedia, you'll see what I'm talking about. So NAND devices, much like disks, allow reads on 512-byte boundaries. However, the operating system often aggregates these together into pages or blocks that are larger. I'm going to be using both of these terms, hopefully blocks a lot more throughout this talk. And they support random access. So unlike magnetic media, where there's a certain inertia associated with the head and a physical location associated with the head, now we don't have any of that. We have a fully electronic device, and we can essentially get any of the blocks on that device relatively easily. So you can see here we have kind of three reads progressing at fairly random locations on the disk, and they work out relatively well. Doing random reads is not that much slower, if at all, compared to sequential reads. Okay. Writes, however, are much more complicated, and they're much more complicated largely because a write actually cannot reprogram the bits to arbitrary values. Writes to an SSD can only reprogram the bits to be updated from 1 to a 0. Okay, that should obviously raise questions. How do you ever set them to a 0? Well, to set bits to a 0, you must erase a region. Now, erasure blocks or erasure units are larger than the actual blocks that we can read and write to on the disk. They're often on the order of 64 kilobytes or 256 kilobytes. So if we want to set any of the blocks within an erasure byte to 0, we have to set them all. So this is really awkward because our unit of reading and writing is relatively small. Our unit of erasing is relatively large and must be applied to all of the blocks within that erasure unit. Okay, what makes it even more difficult is that SSDs have erasure units that have a limited number of erasures. Once you hit that number of erasures, you can no longer erase that that erasure unit on the actual SSD. So you literally have a limited number of times that you can write to effectively all of the regions on an SSD. And if you do it really unintelligently and always write to the same locations on the SSD, then very, very quickly you're going to be unable to use that location basically forevermore, right? So this implies a lot of things about the design of the system. It makes it so that a goal that we have is effectively to do what's called write or wear leveling, which is to spread the erases around the SSD. Erase is an actual operation that you do on the SSD, and you want to spread those across all of the erasure units so that you aren't just hammering one and making it so that you can't use it anymore. Okay, so let's go through some examples to look at what this looks like. Let's assume that second erasure unit that we have there includes blocks with the values A, B, C, and D. Maybe the rest of the disk has data on it. I don't know. Doesn't matter. We're only going to focus on that second erasure block. If what I want to do is write E into that second block, notice I'm saying E here, but really it would be a whole block of like 4096 bytes of information, right? I'm just using the value E as a placeholder for something much larger, right? So how do I do that? I want to overwrite what is in that second block of the erasure unit, but I can't because that would require reprogramming some of the bits from 0 to 1, right? So how do we do this, right? We need to actually erase the entire block. So the erase will zero out everything, and we can at that point do all of our writes of all of the blocks into the blocks in that erasure units to update the values. Notice that we had the values A, B, C, and D, and now we're writing A, E, C, and D. So we're actually only really updating one of the blocks, but we had to write all of them. This is really bad. And if you erase that one unit many, many times, after you do it a certain number of times, you will no longer be able to erase, right? So the goal is, as I said before, to balance out your erasures across the entire disk, which is called wear leveling, so that no one of these erasure units will kind of become unusable. Okay. How do we do this leveling? Well, there are two different ways. They both kind of boil down to the same thing, which is what we'll talk about in a couple of minutes. But we actually have flash devices that do this in two different ways. One is that you have a file system that runs on your flash device that intelligently knows how to try to spread your writes across the flash, therefore your erasures across the flash. That's what we're mainly going to be talking about. A lot of these are placed into a microprocessor on your SSD, and you have what's called a flash translation layer, which is just some logic that's run on your device, on your SSD, that actually does that kind of wear leveling and all of that stuff. It provides a virtual or logical block abstraction to the operating system, but then it remaps to physical blocks. So I'll talk about this a little bit later, but to start out, we're just going to talk about flash file systems. Most of these FTLs end up just kind of being an implementation of a flash file system. Okay, so how does this end up looking? Typically what we want to be able to do is avoid write in place. Write in place, or in place write as it's often also called, is just the idea that we saw before where we would want to modify B to include E. Now what I didn't show before is that to do that you typically need to read out all of the values from the blocks that you don't care about, so that you can actually then erase the block, get rid of all of them, and then write them all back in, right? This is really, really expensive for just updating one block within that erasure unit, right? We have n minus 1 block reads. We don't need to read the one that we're overwriting, hopefully. And we have n writes and 1 erase, right? Here n is just the number of blocks within an erasure unit, right? So this is real bad. We really do not want to do this. As we'll find out later, this is about 10 times slower than the alternative. So what's the alternative? Well, if we avoid actually modifying B and changing it to E and could instead not erase any of these, erase this unit and not overwrite any of these blocks, then we avoid a lot of the overheads. But how would we do this? Well, we adopt one of the things that we've talked about multiple times before into this domain, into this new domain. We use copy on write, right? We know this as cow. Copy on write is the essential idea that we read out our B node, we make whatever updates we want to it, and then we copy it into the new node and effectively have that new block that represents that logical offset in the file into a new block. So what we see is that happening here, where we've essentially copied to make the modification instead of overwritten the block in place, right? Okay, so the big goal of this is effectively that we do block updates not by modifying the block itself, but moving the new version of that block into a new erasure block, therefore preventing us having to erase the previous one. This ends up looking very much like what's called a write log or a write journal, where we continue kind of appending onto the end of this log all of the new modifications. We'll see the example of this, right? The big question that I'm going to ask right now that I want you to think about, because we're going to be revisiting it, is effectively, how do we know when we can reuse that B block, right? Eventually, we're going to run out of blocks on the disk as we keep allocating a new block to write changes into. So eventually, we're going to need to reuse these old blocks. How do we know when we can reuse them? How do we know what those old blocks we can reuse are? This actually is the main complexity in copy on write file systems. So think about that a little bit as we go forward. Okay. So I've introduced kind of the main complexities of solid-state disks. For magnetic disks, we saw that it was a lot to do with kind of like the rotational medium, the head, the physics of all that. Now we see there's this big asymmetry between reading and updating, and there's this weird asymmetry between the size of erasures and the reads and writes, right? Okay, so what are the throughput numbers, right? Okay, so generally a lot of these are all kind of high-level numbers. I've kind of taken ranges of numbers from many different technologies. Some of them are a couple of years old. Again, like the notion isn't what are these exact numbers, it's what are the orders of the numbers relative to everything else, right? Okay, so we have about 100,000 erasure cycles on a lot of devices. This means that we can erase one of those erasure units 100,000 times before we cannot erase it anymore, right? Okay. That notion of kind of writing in place or updating in place, where we read everything, then erase it, then write everything, is about 10 times slower than just a naive write to a block. So this factor of 10 speed improvement is something that we really want to optimize for. So this notion of update in place is something that we do not want to do in the common case. Okay. So how fast is this? How fast are SSDs? SSDs can read and write very quickly at about 200 megabytes per second. There are even exceedingly fast SSDs out there that can go at about 4 gigabytes per second, which is just, flying, which is amazingly fast. The latency on a lot of these devices is on the order of 0.1 milliseconds, which is still many orders of magnitude slower than memory. However, what's interesting is that the throughput figures are actually not that much slower than memory, but the latency is still much slower. Okay, and the high-end size is very, very large. However, when we compare to disks, which we already talked about before, the sizes are still an order of magnitude off, and more importantly, it's much more expensive currently than disk. The cost per gigabyte is converging with that of disk, but it's going to be a while before it kind of breaks even. At that point, disks will probably not really exist anymore. And the reason is because if we look at the overheads and the speeds, well, you see if we're sequentially reading and writing, we can get about 20 megabits per second, which is about an order of magnitude slower than SSDs. However, if we need to randomly go out to disks, oh my gosh, it's 2 orders of magnitude slower, right? So it was already slow compared to SSDs. Now it's 2 orders of magnitude even slower if we cannot use the disks well, right? The latency is on the order, is 2 orders of magnitude slower. So disks, really, their current function is to be cheap, large storage, and that's about it. SSDs are replacing them in most other domains. Okay, so we see that there are weird physical properties of each of these devices, and what I want to talk about now is essentially how we want to design our file system as a function of those physical devices, of the physical devices' properties. So for disks, we've kind of at the highest level abstracted this into rotation good, seek bad, therefore contiguous access good, random access bad. And for SSDs, we have this notion that we want to do write and where leveling, and we want to avoid in-place writes or write in place, right? So I'm going to start out by talking about SSDs since we've already gone through an example of them. Let's just keep the momentum going behind that. Okay, so I'm going to go through a very simple example, which is about a 20-year-old file system, and we'll kind of get more and more updated from there. This is effectively how JFFS works, which is effectively looking at a flash device as a big ring buffer. We've seen ring buffers in many different places in this class, and this is going to be the next instance that we see of it. And it integrates garbage collection into that. So I apologize, by the way, the numbers within here are a little hard to kind of discern. Hopefully you'll get a little accustomed to it. So the big idea of JFFS is that we have a head and a tail, just like we do in any of the ring buffers we talked about in the class. Anything between the head and the tail is active, potentially active blocks. Anything outside of the head and the tail is erased, okay? Now, each of these blocks I've annotated, you see it broken out in the bottom left, as an inode number, which remember could be a file or a directory, the version of the data for that inode number, and the block offset within that specific inode number for that data. So now every single block has this little header that includes the inode number it belongs to, the offset it is within that inode, whether it's a directory that holds a lot of data or whether it's the contents of the file, and then the version number of that data. We haven't seen versions before. We're going to kind of reverse engineer why we might need them here. So from left to right, you see inode 1 with version 0 and block offset 0. This is the first block of data in inode 1. inode 2, we have kind of the same thing, the first block of data. Then we have the second block of data within inode 2. Then we have inode 5, the first block of data there. Then we have the second block of data within inode 3. Then the third block of data within inode 2, and the first block of data within inode 3, and then the 0th block of data within inode 8. What the inodes are is not randomly chosen, it's a monotonically increasing value, but you can imagine that maybe this is a file system where we simply have RM'd some files, so that's why we have gaps in the inodes. Okay, so if we know that we kind of have read into file 2 past the first block, and then we try to write some data into the second block of that inode number 2. So we're trying to write effectively, logically, into the data pointed to by the arrow. Well, we know we can't write to it in place. That's the whole idea on Flash, trying to get away from that so that we don't wear out that erasure unit. So instead, we're going to always write into the heads location. So what we do is we effectively write that new modification into that new location where the head used to be. This might require reading out the contents of the previous block in case the modification doesn't overwrite all of the data, right? So you can see here, when we do that write, we keep the same inode number as we had before, but we increment the version number. And we maintain that same block offset, right? So now, just as we had before, we're writing into inode 2, certainly. We're looking at block offset 1 within that file, the second block within that file. And now we have newer data, so we have a higher version. And if we do many, many modifications to all of the files and directories within the system, we might end up with something that looks like this. Notice I'm kind of manually graying out or shading out kind of the old data within the system, just so that you can see that essentially the data with the highest version number for each of the blocks is what exists in the dark purple. But the operating system might not know that at this point, okay? So at this point, we've modified a whole bunch of data. Whenever we're doing modifications, we're appending them onto the head. This is also called an append-only file system. So at this point, we've gotten to a place where we filled up the flash. You may say there are 4 extra blocks left, but you'll kind of see we need those for kind of the procedure that we're going to go through next, right? So the question is, we filled up the flash. Where do we write new data, right? I have manually colored, again, some of the nodes as the lighter value, which means that they're essentially garbage, which we should be able to reuse them. There are higher versions of that same data somewhere in the system, but we don't know where they are. So we don't know what blocks we can actually reuse, right? An additional thing that I'm not really showing here, but we have not been talking about indices at all. And actually, this version of a file system does not have indices. It has inodes, but the inodes essentially only include the inode number, version, the block offset, and then the data for that inode. There are no indices that tell us where all of the data is on disk. So somehow we need to figure that out. However, I do want to point out that something amazing has happened. We've been doing a lot of modifications to our file system, and we have not done any erases so far, right? So this is great. In terms of write leveling, and in terms of avoiding erases, we're doing great. Okay, so to address that first question, we want to garbage collect those outdated blocks, which means we need to figure out where those outdated blocks are and how to kind of reuse their memory, right? And with respect to not having indices over all of the data in the file system, well, for these simple file systems, they kind of expect the operating system to scan through the entire SSD. By the way, it's fast. And find all of the inode numbers, find the highest number for each of those inodes for each of their blocks. And we simply know that that is the most up-to-date data in that specific block for that file. And then we can maintain data structures in our operating system in memory to track that. But you have no on-disk indices. That means that it is very, very slow to initially build those indices, which is a huge downside to this type of a system. It's actually no longer used essentially because of this. Okay, so let's address that first issue. How do we provide garbage collection? So first what we do is we start from the tail and we iterate through all of these blocks. We find the highest version number of each of the blocks for each of the inodes, and we essentially say if within this erasure block where the tail is, we're going to essentially get rid of that entire erasure block. We're going to zero it out. So any active blocks that are holding the highest version of the data for that block, for that inode, are within that erasure unit. We need to transfer it to the head. And this is why we left that last erasure block open. So we could effectively transfer that last node at the tail into there. And we actually keep iterating through the tail until we fill that last erasure node. So you can see now we've iterated the tail all the way forward till we find the next active node, copying each of those active blocks into that last erasure node as we go, as the arrows have indicated. At this point, we know that we have the new data at the active or at the end of the disk, right? Basically right before the head. We might increment the versions for all of those. This is kind of just details that we could work out. But at this point, we know that between the head and the tail, there is empty data. So what we're going to do is we're going to go through and erase that node. Right? So as we erase that node, now we know that we want to effectively get it so that the tail is only, I'm sorry, let me rephrase. Our goal right now is to make it so that between the head and tail, there is only active data. There is only data that is the highest version numbers for those inodes and for the blocks, okay? So if this is our goal, then we still need to copy more data to the head. So we end up going through and doing that until we get to this point. We have a new head that includes new data, but we still effectively have the last erasure block that we want to get rid of here. So we go through, erase that block. We know that it doesn't include any active data. Copy the last two items to place the tail at a nice clean erasure block that includes only updated information. We update the head and then can erase all of the blocks between the head and the tail. There might be some optimizations here where maybe we don't do this whole procedure all at once. Maybe it's okay for the tail and the head to be separated a little bit. But long story short, we want to periodically provide this garbage collection that gets rid of all of that outdated information on the SSD and leaves us where basically between the head and the tail is only information that is active blocks on disk. And between the tail and the head, we have completely erased data. So this is brilliant. We have essentially gone through and erased most of the blocks on the disk exactly once. We have perfectly wear leveled across the actual disk, right? Sorry, I kind of messed up with my order here. So we have perfectly wear leveled the disk. So that mission is accomplished. However, we have a big problem. We have a big problem because this garbage collection has just copied all of the active blocks on the disk, even those that had not been modified. So I'd like you to take a second here and imagine that if we have a disk that is 80% full and 3% of that 80% of data has been modified, and we go to perform a garbage collection, right? What's going to happen? Think about this for a little bit, pause, come back. Okay, so what happens here is that we've only modified 3% of those nodes. So there are only going to be 3% of this 80% that have this outdated information that needs to be garbage collected. So garbage collecting now is going to copy 80% of the disk when only 3% of it is modified. So you have this perfect, beautiful wear leveling across the disk, but you're also doing many more writes and causing many more erases than is actually necessary, right? So this is not great. And JFS2 modified this idea by essentially trying to reuse many of the different erasure units within the disk. So it would keep track of 3 different lists of nodes. Those that were completely full of active data that is up to date, data that has been overwritten. So some of the nodes, some of the blocks within an erasure unit have outdated information, therefore should be garbage collected, and of course erased blocks. And it would actually try to reuse some of those erasure units that have nodes that should be garbage collected, or some of these erasure units that had mostly outdated nodes within it. So it actually tried to reuse those. Notice when you reuse those nodes, you are causing many more erasures to those nodes. So it would probabilistically try to reuse nodes 99% of the time, versus 1% of the time it would kind of move on within the system. And reuse new kind of nodes between kind of the head and the tail. So this had the impact of essentially not requiring us to overwrite all of the data within the system. It would allow us to keep a lot of the data that had not been modified. We didn't need to modify it, we didn't need to rewrite it, we didn't need to do any of that. But it had the downside of erasing more to some nodes, but it tried to overcome that by probabilistically kind of moving the log on. Look into JFFS 2 if you want to learn more. I'm not going into it in much detail, obviously. And then the big downside of this is that we don't have any indices. So we need to basically read in the entire disk, the entire SSD, to find the updated version of all of the inodes and store all of those kind of records in memory. So on a massive disk, this is completely infeasible because we'd be using too much memory, right? So of course, more modern file systems like UBFS have come along that essentially try to store that index on disk. And this would often be done when we shut down the system. So when we shut down the system and unmount the disk, we would kind of try to rightly index that to disk so it could be read again on boot up. So this basic idea, however, of kind of having a append-only file system, a log file system, or as we've kind of seen before, kind of this ring buffer with garbage collection, is a pervasive idea that spans most SSD management. Okay, so we talked about solid-state disks. Let's kind of go back to disks and see if we can redesign the file systems, not just to have indices, but also to have indices and data tracking systems that very well map to the idea that rotation's good, seeks are bad, right? Sequentially accessing things on disk, good. Randomly accessing things on disk, bad, right? So recall initially that contiguous allocation was the bomb. It was amazing. It was fantastic in every way but the one that actually matters. So it was amazing because data was stored sequentially on disk, which means there was all rotational latencies, no seek latencies, right? Everything is contiguous, fantastic. It allowed us to sequentially or randomly access different blocks in the file equally easily because, hey, everything's contiguous. If I want to access the nth block in a file, I just do some math to figure out where that is on disk and access it directly. Fantastic. Must be the best thing since sliced bread. Except it's not. It's horrible. Nobody uses it. It's horrible. It's bad. Nobody uses it, right? It's actually useless. And it's completely useless because of external fragmentation and file growth, right? External fragmentation was a big problem when we were talking about memory allocation. It's much more of a problem when you talk about file systems because you need to figure out where to contiguously allocate files. And then after you painstakingly place it onto disk in blocks that are very intentionally and carefully chosen, the file grows by twice the size, by 4 times the size, by 8 times the size, and suddenly you can't fit it into that same location anymore, so you need to move it, right? This is no way to manage a disk. So we do not do this. This is real bad. Contiguous indexing as the only mechanism. I don't know of a file system that uses it. I'm sure I'm wrong. I'm sure there's some, but generally it's just not used. But maybe there's a core of a really, really good idea there, right? And maybe we can build on top of it. So the intuition here is that we can index files as a collection of different contiguous allocations. Many of you actually probably happened onto this idea when you were thinking about memory allocation. Why not allocate a range of a file, not just in one contiguous place, but in multiple contiguous places, and then somehow track where all those contiguous places are together in an index. Well, this is effectively what we want to do to maximally optimize for the physics of spinning disk media, right? And this idea is called extents. An extent is the idea that we want multiple contiguous allocations. Each of those contiguous allocations is called an extent of the file or of the directory, right? And the index somehow tracks all of these extents that constitute the file and allows us to figure out where different blocks are within that file. So here's kind of a logical depiction of an extent-based file system or an extent-based index. On the left, we can see that the index is a logical array that effectively tells us that we can walk through the array to see, okay, the first 4 blocks are at this location, the second set of 4 blocks are at this location, the 9th block is at this location, and the 10th through the 16th block are at this location, right? So you can see it's not like a radix trie where we could figure out what index we should look at in this array just by looking at what block we're trying to access. Instead, we kind of need to iterate through the array to keep a sum total of how many blocks we've seen to figure out where, the specific block we're looking at is. Now, how do we actually store this index? How do we implement this index? We can't just have it be an actual array, right? Because how big would it have to be, right? For a very, very large file that has many different extents, it would have to be very large, and we run into the problem that this is kind of a contiguous allocation itself, and we run out of space, right? So we can't do that. File systems don't do this. But we do need some sort of an index that'll allow us to map some sort of a block offset into this logical array that holds these kind of pointers to blocks and the size in blocks of that extent, right? So the question is, what should this data structure look like? What should this index structure look like that can provide a logarithmic lookup for this extent-based index? And I don't know if you've seen it before. I hope so. If you haven't, you should look it up. I'm not going to go entirely into the index structure here, but this is one of those core data structures that you want to know exists. Actually, first, think about it, pause. Do you know the data structure? What data structure would you use? Come back in a sec. Now that you've come back, having deeply thought about the problem, there are many answers, like a red-black tree or something like that. You might think of as tracking these different ranges, but a red-black tree tracks a binary tree, and binary tree is too small to fit into a node to be efficient. So what we want is some sort of a tree that fits each of its index nodes into one of our blocks on disk, right? So B trees or B plus trees or BP trees or B star trees, there are 10,000 different variants of this, are a data structure that's customized towards this. They can try to use up the blocks to hold their different nodes, and they try to track different ranges within, for instance, a file in this case. So as you can see, the top level node tracks the different ranges of different numbers of blocks that are tracked within the B tree, and then it has a number of different nodes. Here, I only have 2. B trees are n-ary trees, so they track many different children. Here I've only drawn 2, and you can see the left node within the B tree tracks the range of the file from 0 to the 234th block within the file, and then that second node tracks between the 234th block to the 8223th block. I kind of generated these numbers randomly, but because extents can be fairly arbitrarily sized, these numbers do end up looking fairly arbitrary in a lot of these trees. So this is exceedingly common. Most next generation file systems that are in use right now, ButterFS, ZFS, all use these, and they all essentially use some combination of extents and one of the B star tree variants. And they even use these, this is an interesting part, on solid state disks. wait, back up. We just talked about SSDs, solid state disks, as using like this weird log structured organization and everything. But now you're telling me that people use these file systems generated for magnetic spinning media that optimize for extents for SSDs? Yes, absolutely, that's what I'm telling you. I know, it's baffling, it's amazing, your head's blown, but it's what happens, right? A lot of the reason is because extents end up mapping relatively well to the SSDs as well. And part of the reason why is because the SSDs are themselves running a small little translation layer that does a lot of the log-based structure, the ring buffer, all of that stuff, copy on write. It maintains all of that information. And on top of that, we implement our file system. So if we look at the entire storage stack in these types of systems, we have our VFS layer, a virtual file system, read, write, open, create, unlink, etc. Behind that, we have a buffer cache. Well, I kind of drew these in a weird order. The cache should probably be below the file system, but okay, sorry. So we have a cache that essentially gives us kind of cache data. We have the file system that is often extent-based and some version of a B-tree based. It has indexing. It tracks free blocks within the medium as a bitmap or as something else. And this is often a file system that is focused on maintaining sequential reads and writes. And when we have sequential reads and writes, that means that the updates for a lot of those writes can very easily proceed for a sequential range of data, and this is often optimized for. And that actually plays very well with a lot of the log-structured optimizations that we talked about for Flash. So what you have next is what's called a FTL, a flash translation layer, which is often a small little microcontroller on your actual SSD. This is not on your main chip. This is on your SSD, on your flash device. And it maintains a mapping between the logical block addresses that your file system uses. Your file system thinks that it's writing to the blocks on the disk, but of course, we've seen this trick before. There's a level of indirection that translates those logical block addresses into the actual physical block addresses. And at this level, the flash translation layer's job is to try to do where leveling, write leveling, and try to minimize the number of erasures that need to happen in the system, right? So you have this weird mashing together of these high-speed file systems based on extents to try to keep everything sequential above a flash translation layer that's taking those sequential writes and mapping them onto kind of this notion of garbage collection and the idea of kind of having these append ring buffer type structures. And then of course you have the physical flash blocks below. So what have we talked about today? We've talked about the physics of devices, and last time we talked about magnetic disks. This time we talked about solid-state disks or flash devices, and we really saw that yes, what do you do when you're trying to optimize for magnetic spinning media? Try to make it so that as much of the file as possible is contiguous, but you can't do contiguous when you can arbitrarily expand the allocation, so you need to use extents, which allow us to have multiple contiguous regions, often indexed by some sort of a B tree that is stored on disk. And we've talked about file systems for Flash that focus on where leveling to make sure that we don't effectively make it so that our Flash device no longer has erasable data, and uses copy on write to actually optimize for that. And we saw briefly, I didn't go into the details, but we saw briefly how these two are combined in a lot of modern systems to try to get the best of both worlds. So I hope this was interesting. I actually did not know a lot of this before, and I looked a lot of this up recently because solid-state disks are, what we all use nowadays, and I had been lazy and not updated these. But hopefully you enjoyed it. Have a good night. Talk to you soon.